Hey folks, today's the last topic of Unit 2, and it kind of puts everything together. So we've been talking a lot. It excludes the rational functions that we just did. It goes back more to kind of the heart of the unit, which was being able to analyze polynomials. So now we're going to be given a function. We're going to use all of our different skills that we've learned to be able to factor, to be able to find zeros, to be able to talk about the end behavior, to talk about multiplicities, to make a decent sketch without using a calculator. So I'd like to start off with having you flip over the notes here, and I'm going to have you try to figure out a couple of different things. Number one, discuss these 6 ways to find zeros. Number 2, discuss the 3 types of multiplicity. And then lastly, discuss the 4 types of end behavior. Now, as you read this, if you have no idea what I'm talking about, that's probably not a good sign. These are kind of the big ideas of this unit. So you're going to have to be doing a lot of studying here in the next couple of days before we get to our test. So pause here, try to fill out as much as you can. When I say discuss, just kind of give examples of each. All right, let's see how you did. So the 6 ways to find zeros. Well, the first way is if our graph is already factored. If our graph is not already factored, the next way is to factor it. Now, these kind of feel like they could be separate, so maybe you made 7, but factoring and quadratic formula to me are the same thing. So then if it's not already factored, you should factor it. If you can't factor it, you should do the quadratic formula. The next style is to solve. Then we can go into our higher exponents. We've got factor out. We've got weird. Now, these are all the factoring techniques we did back in 2.3, I think it was. And then we learned later on about the rational zero test. So how do you identify each one of these? And how can you tell when to apply which one? Well, there's a couple of clues. It's already factored if you have a bunch of parentheses. So if it's already got the parentheses, you know that it's already factored. How do you know when you got a factor or do the quadratic formula? That's when you have a degree of 2. That means the exponent, the highest exponent in the equation is a squared. When do you know when to solve? Well, I know when to solve when there's only one kind of x. So if there's an x that I can try to get by itself, if there's an x and an x squared, I can't get x by itself. But if there's only one kind of x, I don't care if it's squared, cubed, or to the 4th. If I can get that x by itself, I can just go ahead and solve. I factor out is when I've got something in common. So when I've got a greatest common factor, and then I'm going to make a note underneath that then usually you need to then again either factor or do the quadratic formula. After you GCF it, usually you need something after. Then we have weird. Weird is when you've got that pattern of exponents, like exponent of 4, then of 2, then of 0. Or it could be, I'll write it like this: x to the 4th, x to the 2nd, and then just some constant. I'll call that constant c. Now, this also could work for x to the sixth, x to the third, and a constant, but we only do it for, the only ones we're going to see are x to the fourth and x squareds. And then rational zero test is if nothing else works. We have to do the rational zero test if all the other things fail us. Discuss the three types of multiplicities. Well, there's mult1, mult2, and mult3. Mult1 so these all have to do with zeros. So it's the type of zero that you have. In mult1, when the graph hits at the zero, it busts through and it busts through straight. That's a mult1 graph. A mult2 graph comes in, it hits the x-axis, but this time it bounces off and it makes kind of a parabola shape. And then a mult3, it hits on the x-axis, but it makes like a cubed shape. So it looks something like that. So those are the three different defining multiplicities. And then discuss the four types of end behavior. So end behavior is based on two things. We always need to look at the leading coefficient, and then we need to look at the degree. Leading coefficient and degree, leading coefficient and degree, leading coefficient and degree. Okay, so if our leading coefficient is positive, our leading coefficient could be positive and a degree that is even. Our leading coefficient could be positive with a degree that is odd. Or our leading coefficient could be negative with a degree that is even. Or a leading coefficient that is negative with a degree that is odd. And we will get four different end behaviors. I always like to think about it in terms of the leading coefficient first. So if I guess it doesn't really matter. Let's just think about it this way. So these are my positive x's. What's a positive to an even number? Positive times another positive. That means that this end will be going up because it's all positive. This is a negative, and negative an even number of times is positive again, times another positive is positive. So that's one end behavior. Branches both go up. Okay, these are positives. What's a positive? An odd number of times. Positive times another positive is positive. These are negatives. A negative an odd number of times is negative times a positive is negative. So that branch would fall down. My degree is even. These are positives. A positive an even number of times is positive times a negative would be negative. These are negatives. A negative an even number of times, so like a negative to the fifth to the sixth power, a negative to the sixth, or a negative to the second, or a negative to the fourth would turn out to be positive, but then we're timesing by an extra negative, so that branch would fall down. Okay, positives to an odd would be positive, times a negative would be negative. Negatives to an odd would be negative, times another negative would be positive. So this is, 75 to 80% of this unit in a nutshell. If you can understand all these, how these all work, you're in good shape. So now we're going to take these and we're going to apply them to try to sketch our function. So I'm going to look at this. I've got to first figure out where are the zeros, what's the leading coefficient, what's the degree. We're going to use all those clues to make our sketch. So what type of factor? If we're going to try to find zeros, we've got to try to go through our moves. So is this already factored? No. Can we normally factor it? No, because it's an x cubed. So I jump down to my other ones. Is there something I can factor out? Yes. Now here's a dead giveaway. Anytime you have a negative out front, you must take out that negative. It's going to make your life so much easier. So I'm going to take out a negative. Do 8, 8, and 30 have something in common? They all have at least 2. So negative 2, and these all have at least an x. That leaves me with, now I have to distribute build back what I had before. So that'd be 4x squared, subtract 4x, subtract 15. Because I took out the negatives, these signs are going to switch around. Now this is something that I can try to factor. So 4 times 15 is 60. That makes 4. 15 and 4 works. So this is going to be negative 2x times the quantity 2x. 2x. Look, if you're struggling with factoring still, go back and watch my video in Unit 0, or stay after school and we can figure it out. So now we have zeros that I can find the zeros by ZPP in this. So negative 2x equals 0. I would divide by negative 2 and I'd get 0. I'd bump over the 5 and divide by 2, so that'd be 5 halves. I'd bump over the 3, I'd divide by 2, so that's negative 3 halves. So now I've figured out where my graph hits at 0, at 2.5, and at negative 1.5. So those are my zeros. Now I've got to figure out which way does my graph move. Since this is a polynomial, it's going to be a nice smooth curve through all of it, but I don't know which way the ends are pointing. That's why I want to look now at the leading coefficients and the degree. My leading coefficient is negative. My degree is odd. So let's think of what that end behavior would look like. So if I take positive x's, an odd number of times it'd be positive, but I'm timesing by a negative, so this side would be pointed down. Now I'm going to take a bunch of negatives to an odd power, that's going to still be negative, times another negative would be positive, so this side's going to be pointed up. So now I can start my graph. Oh, by the way, how many zeros do I have? 3. What's my degree? 3. So according to the fundamental theorem of algebra, I don't have to worry about any multiplicities here. They're all mult 1s. So I'm going to start my graph up high like this arrowhead is. I'm going to draw, bust through. Now I got to curve and hit the next 0. Bust through because that's a mult 1. Curve back to hit my last 0. Bust through because that's a mult 1. There's my sketch. Is it perfect? I don't know. I doubt it's perfect. We can check. Here's what it really looks like. Negative 8x to the third plus 8x squared plus 30x. I'm going to do a zoom 6. No, I shouldn't have done a zoom 6. I'm going to do a negative 3 to 3. Negative 5 to 5. Here's what the graph actually looks like. Negative 10 to 10. Here's what the graph actually looks like. Negative 20 to 20. Here's what the graph actually looks like. Yeah, pretty close. I should even go up higher. I'm not gonna. I'm sick of typing it in. I'll do it one more time. One last chance. Negative 30 to 30, counting by 3s. Whoosh, whoosh. Dang it, I still didn't go high enough. But you get the idea. So notice I didn't even put any tick marks in this direction because I don't care how high or low it goes. I just need it to have the basic shape, and I'm happy. Okay, let's have you try. Well, we'll do one more together, and then I'll start to throw you to the wolves. So as we're looking at this one, I'm going to look. It's got a negative, so I'm going to definitely take that out. I've got an x to the 4, so this is going to be a higher exponent. So I can take out. I'm going to do a GCF here, factor out. 2, 6, and 36 have something in common, so I'm going to take out a negative 2. I'm going to take out 2 x's. That leaves behind an x squared, a positive 3x, and a negative 18. Negative 2x squared, which I can now factor this into x, plus 6 minus 3. Okay, so here we finally get something interesting. I ZPP this, I bump it over, and I get x equals 0. I get x equals negative 6, and I get x equals 3. Why is this interesting? Because how many zeros are we supposed to have according to the fundamental theorem of algebra? 4. How many do we have? 3. So one of them must have a hidden multiplicity. And I don't know if you caught it already, but this was an x squared, which means this 0 has to occur 2 times. So this is a mult 2. So my graph is going to hit at 0. My graph is going to hit at negative 6. My graph is going to hit at 3 on the x-axis. Now, sometimes it's nice to label these. Go through and label any of the ones that aren't going to be mult 1s, like this is going to be a mult 2. So sometimes it helps do that. If you can do it without it, I mean, you don't have to do it. It's up to you. Now I want to decide the leading coefficient and the degree so I can talk about the end behavior. My leading coefficient and my degree. My leading coefficient is negative. My degree is even. Okay, so positives to an even are positive times a negative is negative, so this branch will be pointed down. Negatives to an even are positive, but then that positive gets times by a negative, so that'll be negative. So both my branches need to point down. So this is a mult 1, a mult 2, and a mult 1. So I'm going to start down here like this arrowhead. Mult 1 busts through. Now I got to curve and come back to this. But when I curve in, I want to curve in a little early because I know I have to bounce off like a mult 2. Now I don't have as much room to go up, so I'm going to make it a quick turn. There we go. I don't care how curvy it is. I care very much, though, that you hit the zeros appropriately. Notice this mult 2 didn't bust through at all. It bounced right off of it and went right back up. Okay, let's have you try the next one. Pause if you haven't yet. Give it a try. All right, so I'm going to do factor out again. 3 and an x cubed. That leaves behind x squared minus 25, which I can then factor. So 3x cubed, x plus 5, and x minus 5, which I can then ZPP. X equals 0. X equals, I'm just going to put those together, plus or minus 5. Now wait, I have 1, 2, 3 zeros. I'm supposed to have 5. That means there must be some hidden multiplicity in here. And there is. My multiplicity here is a mult 3, which are really tough to draw, so take your time. When I get down to this 0, this needs to be a mult 3. So I have zeros at negative 5, positive 5, and 0. Okay, and now I want to talk about the end behavior. I'm not going to write up this leading coefficient and degree thing every time. If you want to, you can. I'm just going to look at this first term. So the first term says odd with a positive. So positives to an odd are positive times a positive is positive. So this branch needs to go up. Negatives to an odd are negative times a positive are still negative. This branch needs to go down. So I've got 2 mult 2s and a mult 3. So, or sorry, 2 mult 1s and a mult 3. So bust through. Now, when you draw a mult 3, it helps to actually go to the mult 3 and draw the like 2 branches of a parabola. Because this one's got to go up so that they can meet here. So I'm going to go like a parabola and then meet that. And then this side, I need to draw a parabola, but I need it to go downward. So I'm going to draw that part as a parabola and then curl it back up. Just take some practice. I stunk at them too. That's a real nice mult 3, Stucky. Thank you. Thank you. Thank you very much. All right. You should be able to finish all these, but let's do one at a time. So pause. All right. Let's see how you did. So what kind of factoring is this? You have to recognize this. This is half the battle. And I recognize that this is weird factoring, which means I factor it like normal. 1 times 64 is 64. 64, that makes negative 20. 4 and 16. So negative 4 and negative 16. So I factor just like normal. X minus 4, x minus 16. But because this was weird, I go back and I put squareds on those. From here, you can break this down again because this looks like dopes. If you wanted to do dopes, you could do it that way. I'm going to do it by ZPP and solving. So x squared minus 4 equals 0. X squared minus 16 equals 0. Bump over the 4. X squared equals 4. X squared equals 16. Who's keeping x from being by himself? Squared. What kills squared? Square root. Square root. Square root is on fire. We don't need no water. We just need a plus or minus. x equals plus or minus 2, x equals plus or minus 4. So I'm supposed to have 4 zeros. I have 1, 2, 3, 4 zeros. Good, so they're all mult 1s. So negative 2 and negative 4, positive 2 and positive 4. Now I'm going to do the end behavior. So I've got an even, positive. So positives to an even are positive. Negative to an even are positive times another positive is positive. So there's my branches. So I can make my sketch now. Mult 1, mult 1, mult 1, mult 1, arrows. Decent. I don't know, that one looks a little bit, those are supposed to be symmetrical. I'm going to have to live with it. Somehow I'm going to have to survive. Ooh, look at how to factor this. Follow your math voice. What's it saying? Even if it's really quiet, it's saying something. Hopefully it's saying factor by parts, because there's 4 pieces, and the only way to factor 4 pieces is by parts. Now, if you didn't think of that, the rational zero test will always work. So I would then break down 18, and I'd start to guess and check. It takes a lot longer to do it that way, but it will work. So let's see now. So this will end up being, these two have a 4 and an x squared in common. That leaves behind x minus 2. The negative has to come out. 9 and 18 have a 9 in common. Now you took out a negative 9, so that leaves behind an x and a minus 2. Those who factor by parts know that that's a good thing because these two are the same. So x minus 2 and 4x minus 9, 4x squared minus 9, sorry. My math voice says that we can go further with this, so I'm going to use dopes this time. I could have solved 2x plus 3, 2x minus 3, and then I'm going to ZPP. X equals 2, and x equals, I'm going to solve those at the same time, plus or minus 3 halves. So we're supposed to have 3 zeros. I have 1, 2, 3 zeros, so we don't have to worry about any multiplicities. 1, 2. Oh boy, this one's going to be right next to each other. We've got 1 at 1 and at 1.5. This is going to be a tight graph. So let's see. We're going cubed with a positive. So positive cubed times another positive is positive. Negative cubed is negative times a positive is still negative. So there's my end behaviors. These are all mult 1s. So bust through, bust through, bust through. Had to turn around real quick. Then last but not least, what color could we do? We haven't done a nice orange. Let's do, it's just regular orange. I know I got to take out a negative. I'm going to do that right away. 4, 20, and 25 do not have anything in common. X cubed, everything's got at least an x cubed, so I'm going to take out the negative, and I'm going to take out an x cubed. That leaves behind a 4x squared, a positive 20x, and a positive 25. This is something that I can factor. Factors of 100 that make 20 are 10 and 10. So that's going to be 2x, 2x. I need to make a 10 and a 10, so that's plus 5, plus 5. ZPP, I get x equals 0. ZPP, I get x equals negative 5 halves. Now, I'm supposed to have 5 zeros. We only have 2. So where are the other ones? That's within their multiplicities. So if I look back at this one's pretty easy because it's a cubed, so that's a mult 3. But this one is a little sneakier, but think about it. If I solved this, I would get this answer, and if I solved this, I would get that answer again. So this is a mult 2. So I have a 0 at 0, and I have another 0 at negative 2.5. I'm going to label these so that I remember that they've got weird multiplicities. This is a mult 2. This is a mult 3. And now let's discuss some end behavior. So these are positive. To the fifth is positive, but times a negative would be negative. A negative to the fifth would be negative, but times another negative would be positive. So there's my arrowheads. So now let's sketch this thing. So a mult 2 means I need to bounce. So I need to come here, bounce up. Now this is a mult 3. These are kind of tough, so I recommend drawing 2 parabola halves. That one wasn't as nice as my one up here. That one looks great. This one's just kind of okay. So now I got to have these 2 halves meet, and then this side just keeps going down from there. There you go. Kind of putting everything together, all the different moves, all the different zeros, finding zeros, all the different solving techniques, all the different end behavior to make it so that we can sketch some of these functions relatively decently by hand. Go get them.